Welcome to this presentation about how we implemented a MuZero knockoff. MuZero is Google DeepMind's most complicated game playing system. So the game we chose to work with is one we made ourselves called Fruit Picker. It's kind of a snake knockoff, just a bit simpler. It's a player has to move around and harvest fruits, gaining rewards for harvesting fruits, and gaining a penalty for leaving the grid, also leading to termination of the game. The actions are up, down, left, and right. To understand how MuZero works, we will start by looking at the most core part, the Mu Monte Carlo tree search. Using 3 neural networks, we can do complex tree searches, even for states of Atari-sized resolutions and large action spaces, which previously were impossible using a model-based approach. So the core concept is that it's model-free, which means that the system has to learn everything about the game itself using neural networks. So that's encoding operations, hidden state transitions, reward, value, and policy predictions. The 3 neural networks that are used by the tree search are the representation network, prediction network, and the dynamics network. The representation network inputs a sequence of real game observations and outputs a hidden state, which is basically the model's interpretation of the game. And the purpose of this network is to encode the sequence of observations into an internal state, and it makes it possible to play games with Atari-like resolutions because the hidden state is a much lower resolution. Now we have the prediction network. It inputs a hidden state and outputs a policy and a value, and its purpose is to predict good values and policies such that the Monte Carlo tree search can pick the best actions. It's crucial for evaluating the hidden states in the search. The dynamics network inputs a hidden state and an action and outputs the next hidden state and a reward related to the hidden state. And it makes it possible to simulate the game using an internal model for the game's dynamics. And it's crucial for exploration and discovery in the Monte Carlo tree search. So we have packed all this into what we call the MuZero network, which has 2 main methods, which is initial inference and recurrent inference. These are used to do the tree search. So let's see how it works. We start by a sequence of real game observations. In our case, we use 2, but you can use as many as you like, which makes sense. We then do an initial inference, encoding the game into a hidden state and predicting the value and policy. Then we can do recurrent inference to explore a new state by inputting an action and the hidden state at the root. And from this, we can do it again, and this is basically the basis of how we explore states using the Mu Monte Carlo tree search. And that's the principles of how the system works. So, an also important concept is self-play, because the system learns from just playing games, no human feedback. So to choose which action we should take, we have to simulate the game using the actual model, and then send frames to the Mu Monte Carlo tree search. So we start by initializing the search tree. We encode the example tree observations into the hidden state and predict the value and policy. Then we simulate actions by using recurrent inference, as we talked about. And we do this again and again. And at the end, the tree search is set up to have visited promising nodes the most times. And we use this to generate a policy distribution at the root node, which we then use to pick the action. And here we should use some randomness to explore, but generally pick the action the network thinks is good. So here we pick the left action. We can see that it gets applied, and now we move on to the next state, and we repeat the same process again. So training the network is essential for having good networks that can actually predict the things we want. So we use reinforcement learning with data from the self-play we just talked about. So for each game we simulate, we save important data to the game object. The game object is responsible for both playing the game, but also storing valuable data we need for creating a training set. So we have observations, which are actual game observations, actions, rewards, child visits. That's a policy distribution of each root node of game state. And we have the root values, which are the Monte Carlo tree search root node values. We will talk about these later. We store these games in a replay buffer object, which has a window size, which is basically how many games it stores. We also have a batch size, which is how many samples we draw from the replay buffer. And the buffer itself, which is a window-sized long buffer of games. And we have experimented with splitting this buffer into 3 sections based on the total game reward, so we can keep good games and not have a replay buffer full of bad games. So the replay buffer picks a random sample. We can see how this works. Basically, it picks, for example, game 5, position 21, and then has the 2 next actions and the 2 next targets. And we do this batch size number of times. We usually use like 128 to 200. The targets we just saw are crucial for creating a loss function. We have 3 of them. We have the reward loss, the value loss, and the policy loss. We can scale these to make sure they have the same size, and do a backward pass on the loss when we have calculated it. This will, in just summary, update the networks behind the recurrent inference and the initial inference methods. So let's see how we can make the reward targets. Probably the most simple one. Here we use the game history of the actual rewards. We can send the rewards through mean square error where we also have the observation and the actions taken, which we send to the dynamics network. Together, this will give an indication of what the dynamics network should predict, and we can use this as a reward loss. So now we have the reward loss. Let's check out the next one. We have the policy targets. we use the Monte Carlo tree search node visit distribution as policy targets. We briefly mentioned this before, but in general, the tree search will favor or visit good states more times than bad ones. So we can simply just take the amount of childs at the root node and divide their visits by total visits, and that gives us a policy distribution. So here we see the example marked with blue. We then send the observation through the prediction network after encoding it, of course. And we can do a cross entropy loss on this to generate the loss for the policy. Now the last one, the value targets. It's probably the most complicated one, so we have to look into a core concept of the tree search called backpropagation. So we also use something called TD learning, which is called temporal difference, where we basically use values from steps ahead. So therefore we're talking about observation 5 when it's observation 2, that is the one we're generating the data for. This is to indicate planning for the networks. So basically we have the prediction and of rewards and values. This is summed and applied the discount to. The discount is used to weight reward versus predictions when you backpropagate, and it's important to choose this factor wisely. Then we do another visit, we backpropagate the value sum of this to the root node, do the same thing again. Then we take the sum divided by visits and add this to root values on the game object. We then can pick the target value as the root value here, and we add it to our target, and we can use a mean square error to calculate the value loss. So now we have all the losses, so let's see how we can backward pass this. We backward pass it through the recurrent inference and initial inference tensors we get when making the predictions. The PyTorch autograd makes sure to calculate gradients for us, and this is how we update the network weights. The representation network has only one network, while the prediction network has two, the policy and value networks. The dynamics network has a transition network and a reward network. So here we can see how valuable PyTorch is to make automatic updates to all of our networks, which are quite complicated. Our network architecture is pretty simple. We're just using normal feed-forward neural networks. For more complex problems, you should at least use convolutional networks for the state interpretation. But since our game is such little, we don't need to do that really. You can pause to see all the details we use. And at last, we have the architecture of the system. So we're just going to go through a normal run from scratch. We start by loading the observations from the environment. The environment is the fruit picker into the game object. We then send the observations to the Monte Carlo tree search, encode the hidden states, and make a prediction. The MuZero network then sends its predicted next state and policies and values to the Monte Carlo tree search. We repeat this and create a policy distribution. We have touched on this a few times before, so I hope you know how it works. When we're done with that, approximately 64 simulations is what we usually use. We send an action to the game, which is going to be performed, and we also store the policies and values on the game object for data generation. We step in the environment, load observations and rewards into the game, and do this cycle until the game is terminated. When the game is terminated, we load the observation, rewards, and policies into the replay buffer, which is used to generate targets for our network trainer. Our network trainer updates weights using PyTorch, and every 100th simulation we store the network in shared storage. And this shared storage is also capable of loading networks if we want to continue with a previous neural network. And repeat this many times to be able to see some progress, hopefully. So our results, we were not able to make the network play the game optimally. It's quite unstable and has some promising frames, like the one we have on the right. But in general, it seems to suffer from a bit of memory loss and not being able to do more than simple edge detection at some cases and guidance towards the fruits. Our largest attempts of training is around 50,000 simulations, and it will undoubtedly outscore a random move approach. Yeah, so this is some data from TensorBoard of our 50K simulation. We can see that the game steps are reduced. Yeah, and note this network had 15,000 initial training simulations, so it had also had been trained from before. So it's 35,000 last steps. We can see that the step counter is moving downwards, and the rewards are not really going in any direction. So the loss is also increasing and the reward loss is increasing. The value loss is stabilizing and the policy loss is increasing. So in general, like other machine learning where if the loss is decreasing, that's a good thing. It's not the case here because it might mean that it has become move abusive, for example, like this example, where we can see that the total reward is increasing a lot, but also the steps. And this indicates that the system just learns to do the same moves to avoid dying. And we can see the loss is decreasing here. Total loss, the policy is actually increasing, but the other two are decreasing because it's just predicting 0, basically. So we can't trust a loss function to be an indicator of the system actually doing good. So here's the credit page. Thank you for watching.